we are discussing the topic of bending moment and shear force in continuation with what we did last time. So before doing that, let us discuss a few things. This is a beam and it is loaded with a uniformly varying load, or distributed, not varying load, uniformly distributed load, small w per unit length, and we have taken a small piece of it at a distance x from this end A and B are the points of support, maybe simply supported, and the length of this portion is dx at a distance x from end A. So you can see the bending moment and shear force, they are acting on this. We have taken this positive sense, F plus dF on this end, and dF is the shearing force on this end as we move from this part to this end to this end. M is the bending moment here, and plus dm is the bending moment here. So now if we take the moment of the forces about the point C. C is the midpoint of this portion with the length of which is dx. Now why we are doing this? This is very important. We are doing this to show the variation of shear force and bending moment and the rate of loading. W in terms of rate of variation of F, rate of variation of M. This you will find very important when you solve the questions in which the loading diagram will not be given to you, bending moment or shear force diagram will be given to you, and you will have to find or draw the diagram showing the load on the beam. So if I take the moment about point C, then sigma of M about C is 0. So this gives us moment of F about this in this clockwise direction. Let us take this as positive into dx by 2. Distance from C to here is dx by 2, and this F plus dF is also in the same direction, clockwise direction. So plus F plus dF into dx by 2. What about the moments? Moment M is in same direction, whereas M plus dm is in opposite direction. So plus M equal to M plus dm. So we can write, solving this and this will add. So f dx and df into dx is a very small term, can be neglected. M cancels out, is equal to dm. So this gives us F is dm by dx. The shear force is equal to rate of change of the bending moment. Now if I write the condition for net load on this is 0, sigma F is equal to 0. So the net downward load is W into dx, the load which is distributed, W per unit length into length dx, and another downward force is F plus dF is equal to upward force F. So this gives us W is minus dF by dx. The negative rate of change of the shear force is equal to the rate of loading in case of uniformly distributed load, and this can also be written as equal to, if I use this, minus d2m by dx square. Now if we have at some point F is equal to 0, that means dm by dx is equal to 0. If F equal to 0, so dm by dx equal to 0, that means M will be minimum or maximum at that point. So whenever the shear force becomes 0, the bending moment will be minimum or maximum at that point. And we can write this in another form, say from point A to point B, dm is f dx. This gives mb minus ma, that is the rate, the change in bending moment, and this you have to find from the bending moment diagram. between any two points A to B, that is given by the diagram of the change in shear force diagram A to B. So the area under the shear force diagram between two points gives us the change in the bending moment or between these 2 points. This is one relation. Similarly, we can write from this relation dF is equal to minus W into dx. We can integrate this also, and for loading between 2 points A and B, Fa minus Fb, this is integral of W dx A to B. So the area under the load diagram, when we have uniformly distributed load W per unit length, that will give you the change in the shear force between those 2 points. And also I can write from this by using this relation MA minus MB. Now we have second derivative, so we will use double derivative A to B. So these relations, they are quite helpful when we have to calculate the shear force and bending moment for a given beam. Now after this we can discuss the shear force and bending moment diagram by taking some examples. By taking the example of a cantilever beam, which is simply supported. The length of this cantilever is L. This is free end, this is the fixed end, and in this case, if we neglect the weight of the cantilever, then you can see that there is no shear force or there is no bending moment acting on it. But is it true? The answer is no, because the shear force and bending moment, because of its own weight, may be neglected for the purpose of analysis, but actually they create the shear force also and the bending moment also. So we apply a load W on it at the free end. This is free end, this is fixed end. And one more thing I would like to tell here, that it is not necessary that this load is acting at this point only. It can be acting at any point along the span, and there may be more than one loads which are present along the span. There may be other types of loads also. So as we discussed in the previous discussion class, what this load is doing here. Suppose, as I told you, my hand, this is the fixed point, this is the free point, this is like a cantilever. As I told you that if I ignore this hinge joint, because this is a hinge joint, so assume that this is a straight cantilever without any hinge joint, and what happens at the hinge joint is the bending moment is not transferred. So the load acting here for the purpose of equilibrium, a reaction is also acting at the fixed point to stop the beam from being sheared. So this reaction is R, this is the fixing reaction, and this W about this point, this creates a moment which will be maximum here, maximum bending moment, W into L. The direction is anti-clockwise, and to count another fixing moment is acting here naturally in this opposite direction to the moment of W about this point B. So M is the fixing moment, W into L. So if you start to draw the bending moment and shear force diagram from this end, so first of all you have to find the fixing moment and the fixing reaction. So it is not difficult, but to avoid this you can start from this end. Now how to do this? Take a section here. Take a section, and this cross section shows that the force acting on this side is W on the left side. Take a section in such a way that there is a load on left side to this. If there would have been more than one forces, W here, W1 here, then I would have taken the section between these two, so that there is a force on left side and rest on the right side. Now on the left side of this, which load is present? Load is only W, and it is trying to shear the beam in this direction. This portion would come down, and this slips with respect to this like this. The shearing will be somewhat like this. Shear force F and the shear force in this direction. So as per our discussion previously, this type of shearing is negative shear, which produces a hogging or negative bending. So what is the shearing force? W is, to the left side of this is minus F, and this remains constant for the entire length because there is no other load to this point B. So this is constant. So if I draw the diagram, W is equal to F is equal to minus W. Shear force is W in the negative direction as per our convention. This is negative. So the shearing force is constant. So draw a rectangle. This is W minus, and the length is L. This is the shear force diagram. Now we can draw the bending moment diagram also. Let us write the equation of bending moment at a distance x about this section. The section is at a distance x from the free end. So you have to do nothing. You have to take the moment of this shear force about this section. So W about this section is creating a moment in this direction, which as per our discussion, because of the hogging bending moment, is negative, which we have discussed previously. So minus W into x. So at x equal to 0, bending moment mx is 0. At x equal to L, it is maximum, minus W into L. So this is the equation of a straight line, y equal to mx on the negative side. So here it is 0, and here it is maximum, W into L. The length is L. This is how you can draw the bending moment diagram of this cantilever. So this is very simple to draw the shear force and the bending moment diagram for this cantilever. Now after this, let us take the example of a cantilever with a uniformly distributed load over its span. And here we assume that the lateral dimensions of this cantilever, they are small enough as compared to its cross section. That means length is quite large as compared to width and breadth. The cross section is like this, maybe circular, square, triangular, and this type of cross section, what type of cross section it should have for the purpose of bearing the maximum bending stresses, shear stresses. This will be discussed later on in the chapter of the bending stresses. There are various types of cross section which are generally used. So here it is having the uniformly distributed load, W per unit length. L is the length of the cantilever. So what is UDL? Just like you have this beam in the roof and there is a wall on it, this wall is just its weight is 500 tons. So 500 divided by the length of the wall, that is the UDL acting on the entire beam. So this we have shown here. Now this UDL is also acting at the center of the beam. This is supposed to be effectively acting at the center of the beam for the purpose of calculations. Now let us take again, and in this also a fixing moment and the fixing reaction will be present here. So this will be the case every time. Now let us take a cross section at a distance x from the free end. You can also write down the magnitude of fixing moment and fixing reaction. What is the net downward load? The net downward load is this total load, W per unit length, W into L. So this fixing reaction will be W into L, and what is the moment of this load? Load is acting at the center, W into L, multiplied by distance from the center of this point. So W into L multiplied by L by 2. So this is the fixing moment at this end. So now we can draw the shear force and the bending moment diagram. What is the shear force about this section? The load just towards this left side of this is the load included in this portion of length x, and this is of course negative, so minus rate of loading into length minus Wx. Now see the graphical variation of this. This will be a obviously straight line, y equal to m into x. So at x equal to 0, no load and no shear force. At x equal to L, the shear force is maximum, so this is a straight line. So W into L. And the bending moment produced by this will also be negative as per our convention. So what is the bending moment? Mx here is negative, so minus moment of this force about this. So this load is acting at the center of this at a distance x by 2 from this end, x by 2 from this end, and load included in this is W into x. So minus Wx into x by 2 minus Wx square by 2. So this is a parabola. The variation shown will be of parabolic in nature, because x square equal to minus ky, this is a parabola this type. So you can now draw the variation of this bending moment. At x equal to 0, the bending moment is 0. X equal to 0, it is 0. And at x equal to L, the bending moment is WL square by 2. This is the bending moment diagram. So we have used this portion of this parabola. So this is how you can draw the bending moment and shear force diagram in case of a cantilever having uniformly distributed load over the entire section of the cantilever. Similarly, we can take other types of loading also. We can discuss other type of loading also. Now suppose we have a cantilever which is having uniformly varying load. We show the UVL like this. The cantilever is fixed here. This is the free end, length is L, and the rate of the loading is variable, being maximum at this fixed end W per unit length. At free end it is 0. Now we have to draw the shear force and the bending moment diagram for this. First of all, let us draw the shear force diagram. So take a section here at a distance x from this free end, and we have to find the load acting to the left of this section on this side. That will be equal to the area under this loading diagram from x equal to 0 to this point x equal to x. That is area of this triangle. If I name this triangle, this point is A, B, C, D and E. So shear force at x is equal to, with the negative sign, area of triangle ADE. So that is equal to 1 by 2 into base into height. So we know the length of the base is x, but we don't know here the rate of loading, intensity of loading. Here it is 0, here it is W per unit length. So we don't know this parameter, this height here or breadth. We have to calculate this. So this you can do by using the principle of similar triangles. So ADE and ABC are similar triangles. So I can write that BC divided by DE is equal to AC divided by AE. So this gives us W by L is equal to BC divided W by, sorry, this is suppose B here, DE is taken as B per unit length. So I have assumed that the rate of loading here DE is equal to B per unit length. So I have written this as B. Let me write DE is B per unit length is equal to L by X. So B is W X divided by L. So shear force to the left of this section is Fx at a distance x from here is minus into area of this triangle AD, half into base AE into DE. So minus half x into Wx by L. So minus Wx square by 2L. So this is again the equation of a parabola. At x equal to 0, the shear force is 0. At x equal to L, the shear force is maximum. And this is a parabola, this type, negative. And here at x equal to L, the shear force is minus W L square by 2L minus WL divided by 2. So this is how you can show the shear force diagram. Now the bending moment. Mx, the moment of this shear force about this section. Now we know that in case of a right angle triangle, this is the center of gravity or center of mass of the triangle. This length is L. So this is, this point G is lying at a distance of L by 3 from the perpendicular, and from the free end this will be equal to 2L by 3. So Mx is force multiplied by distance of the point of application of this force. This point, say this point is O from this section. So this is x divided by 3. This total is x, this is x by 3, this is 2x by 3. So minus Wx square by 2L into x by 3 minus Wx cube by 6L. This is a cubical parabola. And if you draw this at x equal to 0, this is 0. At x equal to L, this is minus WL square by 6. This is the bending moment diagram, and this is the shear force diagram. You can also calculate the fixing moment and the fixing reaction at the fixed end. The fixing reaction will be equal to the total load. Total load is equal to area of this triangle. So if I calculate the total load here, this is the fixing reaction. Area of this triangle half into L into W. So this is WL by 2 equal to R. And fixing moment in this direction, M, equal to moment of this load. This is acting at the center of gravity of this triangle at this point, which is L by 3 distance from this end. So WL by 2 into L by 3. WL square divided by 6, which is clear here. The fixing reaction will be opposite to this in upward direction, so it is positive. It is negative shear force maximum, and here this is negative bending moment, and here this will be in opposite to this. That means positive moment, fixing moment in magnitude. These two are same. So this is how we calculate the shear force and bending moment for a cantilever having different types of loadings. Similarly, we can do this for the beams that we will be doing in our next discussion. Simply supported beam and other types of beams.